Hello and welcome to Controllerstech. This is the 6th video in the STM32 USB series. Just like the previous videos, today we will continue using the STM32 in device mode. We have already covered how to use the USB device in Communication Device Class, Human Interface Device Class, and Mass Storage Class. Today, we will see how to use a composite class, where we will combine two different classes that both share the same USB port. For this demonstration, we will combine the CDC class and the HID class. The STM32 will emulate as a game controller, and at the same time, it will send data to the computer using the CDC class. Before we proceed, you need to make sure that both CDC and HID Gamepad are working separately on the STM32. I have already covered both of them in the previous videos. I have also downloaded their projects, and we will need some files from these folders later in this video. Now let us take a look at the connections. The CDC class does not require any specific wiring, it communicates entirely through the USB. For the HID Gamepad part, I have connected one analog joystick to the STM32, just like I explained in the HID video. The X and Y axes of the joystick are connected to ADC1 channel 0 and channel 1, and the switch button is connected to pin PA2, which we will configure as an input in STM32 CubeMX. The joystick is powered with 3.3 volt directly from the STM32 board. Now that we understand the connections, let us open STM32 CubeMX and create a new project. I am using the F446RE, just like in the previous videos. Let us start with the clock configuration. The WeAct Studio development board I am using has an 8 MHz crystal on it, so I will enable the external high-speed crystal first. We will then use the PLL to run the system clock at the maximum possible speed of 180 MHz. Next, go to Sys, enable serial wire debug. Now let us start with the ADC configuration. I will skip the detailed explanation here, as I have already covered it in the HID Gamepad video. Enable channel 0 and channel 1 of ADC1, which is where the X and Y axes of the joystick are connected. We will set the ADC resolution to 8 bits. Since we are using two channels, we need DMA to read both channels efficiently. So I am enabling DMA for ADC1 in circular mode, and making sure the data width is set to byte, since our resolution is 8 bits. Now go back to the parameter settings and change the number of conversions to 2, since we have two channels to convert. The scan conversion mode will be automatically enabled. Now enable continuous conversion mode and DMA continuous request as well. Also make sure the end of conversion selection is set to end of all conversions, so the DMA interrupt will only trigger after both conversions are complete. Now let us configure the channels. I will increase the sampling time to the maximum, which is 480 cycles. This slows down the conversions and reduces the rate at which interrupts trigger. That is all we need to configure in the ADC. Now configure pin PA2 as GPIO input. Then go to System Core, open GPIO settings, and enable the pull-up for this pin. This way, the pin will be pulled high by default, and when we press the button on the joystick, the pin will be pulled low. This is how we detect a button press. Now go to Connectivity, open USB OTGFS, and enable it in device-only mode. No additional configuration is needed here. Next, go to Middleware and open USB Device. Here we will select the class. Since we are using two classes, let us start by selecting the Communication Device class. STM32 CubeMX does not allow us to configure both classes at the same time, so we will need to do the rest of the configuration manually later in the code. Now, since we are using two classes, CDC and HID, we need to set the maximum number of interfaces correctly. Set the maximum number of interfaces to 2 for the two classes. If it does not work, we will increase it later in the code itself. Let us also reduce the CDC RX and TX buffer sizes to 1 KB. That is all we need to configure here. Now go to the clock configuration tab. You will notice an error, and this is because the USB is currently receiving 180 MHz. We need to adjust the PLL multipliers and dividers so that the USB clock receives exactly 48 MHz. That is all we need to configure in this project. Now provide a name for the project, make sure the toolchain is set to STM32 Cube IDE, and click Generate Code. The project has been generated, so import it into STM32 Cube IDE now. Alright, the project has been imported, and here is the main file. Before working on the composite class, we need to make sure that the CDC class is working correctly on its own. I am defining a custom write function, so that I can route printf data through the CDC class. I have already explained this in the CDC video earlier in this series. Inside this write function, we simply call the CDC transmit function, which will send all the printf data through the CDC class. Inside the infinite loop, I am printing a simple string every 1 second. Now scroll to the top of the file and include the USB CDC if.h header file in order to use the CDC transmit function. Also include the standard IO header file in order to use the printf function. That is all we need to do here. Let us build the project. There are no errors, so let us flash it to the board. Open the serial console. You will notice that there is no USB port available at this point. Once the project is flashed, you can see the USB port is now showing up in the serial console. Let us connect to this port, and you can see the string is printing every 1 second. Our basic CDC class is working correctly. Now we can proceed with setting up the composite class. We need to copy the composite class library into our project. You can find this library inside the STM32 Cube installation folder, which is generally located inside your user directory. On Windows, you can find it directly under your username. If you cannot find this folder, you can also get these repositories from ST's GitHub page. I will leave the link in the description of this video. Open that folder and look for the library files under the board series you are using. For example, I am using an F4 series board, so I will look inside the F4 folder. Navigate to Middleware, STM32 USB Device Library, Class, and here you will find the Composite Builder folder. Let us copy this entire folder and paste it into the same location inside our project folder. Now we have two classes in our project, CDC and Composite Builder. We also need the HID class, but instead of getting it from the STM32 Cube installation, I will get it from the HID Gamepad project, because that project already contains the Gamepad device descriptors that we created in that video. So open the Gamepad project, navigate to Middleware, STM32 USB Device Library, Class, and copy the HID folder. Paste it at the same location in our current project folder. Now we have all three classes in our project, CDC, Composite Builder, and HID. Let us open the USB Composite Builder.c file. You will notice that this entire file is grayed out, and that is because this use USB Composite is not defined yet. We need to define it first. We will add all our definitions inside the USB configuration header file, so let us open it and define use USB Composite. Let's build the project once. We have some errors, but ignore them for now. Go back to compositebuilder.c file, and you will see that the entire file is now active and no longer grayed out. Now open the compositebuilder.h file. Here you will see that we need to define which classes we are using. We will add these definitions inside configuration file as well. Since we are using HID and CDC, we will define both of them. Let's build the project again, and now inside compositebuilder.h you should see that both the CDC and HID inclusions are active. The next thing we need to define is USB Composite Use IAD. On Windows, this is required for the operating system to correctly identify and separate the two classes sharing the same USB port. Without it, Windows may not be able to distinguish between the CDC and HID interfaces. We will add more definitions to this file later. Right now, you can see there are around 9 errors, and most of them are showing in the USB CDC file. Let us take a look. Here is the first error. It is on the CDC setTX buffer function. This function was working correctly earlier when we were using CDC on its own, so why is it suddenly an error? If you open the declaration of this function, you can see that the original function we used earlier is no longer valid when using the composite class. It has been replaced with a new version that has one additional parameter at the end, which is the Class ID. We cannot fix this just yet, because we do not have the Class ID for CDC. Once we register the CDC class manually later in the process, we will have the Class ID and we will fix all these functions at that point. The remaining errors in this file will all be fixed in the same manner. Now we need to define the endpoints for both the CDC and HID classes inside configuration file, so that all endpoint definitions are in one place. Let us start with CDC. Open CDC header file and you will see that the CDC class uses 3 endpoints, all defined here. We will copy these endpoint definitions and move them into configuration file. Let's build the project again. You will notice that the endpoint definitions inside cdc.h are now grayed out, because they are already defined in the configuration file. That is exactly what we want. Now we need to do the same for the HID class. Open HID header file and copy the endpoint definition into configuration file as well. However, there is an important thing to note here. Since we copied the HID files from the previous HID-only project, the HID endpoint is currently set to 0x81. That endpoint is already being used by the CDC class, so we cannot use the same one for HID. I will change it to the next available endpoint, which is 0x83. This is exactly why it is important to define all endpoints in one place, so we can easily spot and resolve conflicts like this. That completes all the configuration file changes for now. As I mentioned earlier, the HID device descriptors are already defined in the HID files we copied from the previous project. You can see the gamepad descriptors are already there, so we do not need to define them manually. Now open usbdevice.c file. Inside this file, you will find a function called MX USB device in it, which handles the initialization of the USB device. This function currently contains 4 steps: initializing the USB peripheral, registering the CDC class, registering the interface for CDC, and finally starting the USB device. Out of these 4 steps, we need to modify the 2 in the middle, because those 2 depend on which class is being used. For reference, if you open the same file from the HID project, you will notice a difference. After registering the HID class, there is no interface registration step. This is something we need to handle carefully when initializing the USB device in composite class mode. We will start by making changes to the class registration. Let us scroll to the top of the file. Before we register the classes, we need to include the composite builder and HID header files in our project. To do this, right-click the project and open Project Properties. Go to CC++ Build, then Settings, and under the MCU/MPU compiler section, open Include Paths. You can see that the CDC class is already included. We need to add the include folders for the composite builder class and the HID class as well. Once both are added, click Apply. Now we can include both header files. Add USB Composite Builder and USB HID header files at the top of this file. Next, we need to define the endpoint arrays, as these will be used during class registration later. Define a separate endpoint array for CDC, and a separate one for HID. The CDC array will include all 3 endpoints, whereas the HID array will include only one. Now let us continue with the USB device initialization function. We need to register the classes using the Composite Class registration function. You can find this function in USB core.c file, just below the USB register class function. It is called register class composite. We will use this one instead. Let me copy this function into our initialization code. The first parameter is the device handle, which is already declared earlier in the previous function. The second parameter is the USB device class type structure, where we will pass the CDC class since we are registering it first. The third parameter is the composite class type, which is also CDC but uses the composite specific definition. The fourth and last parameter is the endpoint address array, which we have already defined above. Now we need to do the same for the HID class. Copy the same function call again, and replace CDC with HID. After registering both composite classes, we need to set the class IDs for each class, and then register the interface for CDC. To set the class ID, we call composite set class ID function. This function takes 3 parameters, the USB device handle, the class type, and the instance number. For CDC, the instance is 0 since this is the first and only CDC class we are registering. Since CDC is the first class whose ID we are setting, its class ID will automatically be 0. After setting the CDC class ID, we register the interface for CDC. Here we can use the same function, which was generated by the CubeMX. Next, we set the class ID for HID in the same way. Its instance is also 0 since this is the first instance of the HID class. And since this is the second class registration, the class ID for HID will automatically be 1. The class ID increments each time you call setClassID function for a different classes, so CDC gets ID 0 and HID gets ID 1 automatically. It is also worth noting that the setClassID function returns the class ID, so you can also create separate variables to store the returned values, and use them throughout your project wherever the class ID is needed. I will include that approach in the final code. You can also read more about this method in the article linked in the description of this video. Finally, we call USB start function to start the USB in device mode. Let's build the project again. We still have some errors, so we will fix them in cdcif.c file. Starting with the CDC setTX buffer, as I mentioned earlier, this function now requires one additional parameter, which is the class ID. We will pass 0 here, since that is the class ID for CDC. We do the same for all the other CDC functions in this file. Now when we build the project, there are no more errors. Everything has been resolved. Let us now write the rest of the code in the main function. Since the CDC class does not require any additional code, we will now write the HID part. I am going to copy the relevant functions from the HID Gamepad project, since that is what we are implementing here. Let us copy all those functions and paste them in their relevant locations inside the main file. Inside the infinite loop, we will add one more thing. After the HID report is sent, we will print the HID buffer data on the serial console using the CDC class. This way we can verify that both classes are working at the same time. The HID class will be sending gamepad data to the computer, while the CDC class will be printing the same data on the serial console. Let's build the project. We have some errors, and that is because I have not included the HID header file at the top of the main file. Include the HID header file here and rebuild the project. We still have one more error, and this time it is in the HID send report function. Just like the CDC functions we fixed earlier, this function also requires the class ID as an additional parameter in composite mode. We will pass class ID 1 for HID. Now let's build the project again, and there are no more errors. Let's flash the project to the board. Right now the USB is not connected, and the serial console does not show any CDC device. I will connect the USB now, and you can see a new device appearing in the serial console. Let's connect to it. You can see here there isn't any data being printed. That means something is not working correctly. Let's go back to the main file. Here comment out the HID send report function, and flash the project again. Now you can see the data is printing on the serial console correctly. The X and Y values are changing as I move the joystick, and the button data is also working. So the CDC class is working fine on its own. After some debugging, I found that the HID send report function was getting stuck. The issue is in the USB configuration source file. If you look at the USB LL initialization function, you can see that the TX FIFO is only configured for 2 endpoints, 0 and 1. But right now we are using 4 endpoints in total, 3 for CDC and 1 for HID. So we need to configure the TX FIFO for endpoints 2 and 3 as well. I will add 2 more function calls to set the FIFO size for endpoints 2 and 3. However, make sure you do not allocate too much memory here, as there is a total memory limit for the TX FIFO. You can check the reference manual of your microcontroller to find this limit. For the F446, I believe the limit is 320 words, which needs to be divided between the 4 endpoints and the RX FIFO. This RX FIFO is shared among all endpoints and handles all incoming USB data for the device, hence it needs to be larger in size. Now let's go back to the main file, uncomment the send report function, and flash the project to the board again. This time, the data is printing on the serial console. Let's also open the Gamepad tester website, and you can see the gamepad is now being detected as well. The X and Y axis movements are being reflected on the gamepad tester, and the same values are being printed on the serial console at the same time. This confirms that both the HID and CDC classes are working simultaneously over a single USB port. Our STM32 is successfully operating in composite class mode, combining CDC and HID into one, and the computer is detecting both correctly. That is all for this video. I hope you found it useful. In the next video, we will see how to use a mouse and keyboard together using the same HID class, where data from both will be sent to the computer through a single USB connection. That is all for today. You can download the project from the article linked in the description of this video. Leave comments in case you have a doubt or suggestion. Keep watching, and have a nice day.